point masses m1 and m2 are placed at the opposite ends of a rigid rod of length L. This is the rigid rod. The total length is equal to L, and the m1 and m2 are the two masses are placed at the end here. M1 and m2 are placed here at the end. The rod is to be set rotating about an axis perpendicular to each. The rod is placed so that the axis is perpendicular. Whatever the axis is there, this axis is perpendicular to this rod and it is rotating about each. The position of the point P on this rod through which the axis should pass so that the work required to set the rod rotating with the angular velocity omega naught is minimum is given by. That means we need to find here the work minimum. So the work minimum, when it is happen, that means when the work done, that is equal to half into I into omega square, that is for the rotational kinetic energy. In that case, we will get the work minimum. Okay. When the I minimum will happen, then the work minimum is also there. When that moment of inertia, when it is minimum, it has happened at the center of the masses, or the center of the masses, which is also we have axis that is perpendicular. When this is perpendicular, then the center of the masses, then this moment of inertia I will becomes the I minimum. Then we will get the work minimum. Then we can write the kinetic energy of the system. That is the kinetic energy of the system. We can write it as half into I omega square, which is equal to half into m1 into x square plus m2 into L minus x whole square into omega square. Then the work required, that is W is equal to delta, that is delta kinetic energy, which is equal to half into m1 x square plus m2 times L minus x whole square into omega square. Then for what minimum work is equal to, we differentiate this work with respect to x, then we get the answer. That is dw by dx is equal to 0. Then d by dx of, we can write it as m1 by differential, then m1 by 2 into x square plus m2 by 2 into L minus z whole square into omega square would be equal to 0. Then we get into x plus n2 into L minus x into minus 1 is equal to 0. Then my into x plus m2 into x minus m2 into L is equal to 0. Then we get the answer x is equal to n2 into L divided by m1 plus m2, where this x will get, that is x is here, x is here. Then this is the location of common of the 2 point masses. Then x, this distance is m2 into L divided by m1 plus m2. So m2 divided by m1 plus m2, option A is the right answer.